Hi everyone. So this is part of my attempt to make a math exposition video. I have put lectures online because I am an assistant professor, and so I teach, and all the classes that are going on right now are online at my institute. But this is slightly different because I never put these things on YouTube. And I thought that, so I'm a discrete probabilist by training, which means that I work on sort of the interface of combinatorics and probability, which has lots of applications, say in computer science, and also takes a lot of, elements from computer science, from mathematical logic, from automata theory. It studies random graphs, various aspects of random graphs. And it's a fun area. And this is for this 3 blue, 1 brown, they put forth this idea of like creating math exposition videos. But now that I have started, I might actually continue doing this little by little. I was the PhD student. I was one of the PhD students of Professor Joel Spencer, who is one of these, the pioneers of this field. Of course, this field sort of started out with Paul Erdős, and alongside him, Alfred Renai. And they started out by studying evolution of random graphs. So with Professor Spencer, I studied quite a bit of this topic, but of course this topic is, first of all, relatively new, so there is a lot to learn, and it's very fun. It's almost, a lot of it is almost feels like recreational mathematics. Have a lot of fun solving these puzzles, except that they're very, very extensive puzzles. So. And I'm going to follow mostly the book by Nogalon and Joel Spencer. It's known as the Probabilistic Method. Let me show you a copy of the book. So this is what the 3rd edition looks like. Okay. I think the 4th edition is available on Amazon. So. And I will be, if I can continue doing this at a pretty much regular pace, then I would be also referring to other sources, sort of pooling resources and making more and more videos, especially focusing on random graphs and their various properties. Okay, so today, whatever I'm going to talk about, you do need to have a basic idea about probability. You have to have some basic training about probability, what probability means, the most fundamental of definitions. You do need to know what expectation is, what a random variable is, first of all, what it means to say the distribution of a random variable or the expectation of a random variable, but not much more than that. And this is particularly going to be enjoyable for those people who love graph theory, who love discrete mathematics, who love combinatorics. Okay, so I'm going to start by sharing my screen. So let me start doing that. So here it is. So let's see. How do I, oh yes, I can move this and I can remove this. Okay, great. So hopefully this is visible to all of you. And I am going to, so I named this the first footsteps into the world of probabilistic methods. So let me just plunge straight ahead. What is this topic all about? So basically the idea is that you take a problem that comes from, one of the many areas of mathematics. It could be from graph theory, could be from combinatorics, could be from number theory, could be from other areas as well, computer science included. And the problem a priori does not really have anything to do with probability. It's a problem that does not involve any randomness whatsoever. But what we tend to do if it's at all possible, is incorporate a suitable probability measure space into such problems, sort of like injecting probability, some people say, into such problems. And this allows us to often come up with very, beautiful solutions. Like beautiful is the only word that I can use here. Solutions that are probably going to prove pretty difficult to show without the aid of probability. Sometimes we come up with partial solutions because a lot of these problems are all about, the problem itself is like very complex, very, or it's kind of vast, so you can only do some incremental solutions. So sometimes using probabilistic method actually helps. And sometimes we come up with amazing inequalities and bounds that sort of, again, are sort of give us stepping stones for improving those bounds, for making progress in these areas. So because this is sort of like a video for like beginners who haven't been introduced to probabilistic methods, I wanted to keep this, first of all, short. Hopefully this will be short. And I also wanted to sort of limit the contents of the video to a couple of examples, just a couple of examples to show you how probability can be suddenly brought into a problem that has a priori nothing to do with probability at all. And using probability, we are able to get nice bounds. Okay, so I'm going to start off with Ramsey numbers. So maybe a lot of you are very familiar with this, but I'm going to still describe what a Ramsey number means for the sake of those who haven't seen this. It's one of these, very famous objects in combinatorics or in graph theory. So basically, you are given a graph G, and I'm going to refer to the vertex set of the graph as capital B of G, and the edge set of the graph as capital E of G. And I'm going to consider two colorings of the graph. What is a two coloring of a graph? So keep in mind that when you talk about coloring of a graph, it could either mean coloring of its vertices or coloring of its edges, okay? In this particular situation, we are talking about edge coloring, okay? So because it's a two coloring, so there are two colors involved, and I'm going to take them as red and blue. And to each edge of the graph, so to each edge E of capital E of G, I am going to assign either the color red or the color blue. Okay, so this you can, if you are comfortable with it, you can formally think of this as a function f that goes from the set of all edges capital E of G to the set red comma blue. Okay, so this is what a two coloring is, and this is what's going to constitute the crux of the problem. So let K sub n denote the complete graph on n vertices. Okay, again, this may be something that you have seen before, because K sub n is actually quite a standard notation for complete graphs. What this means is that you start with n is any positive integer, and you start with n labeled vertices. Okay, so let's say 1, 1, 2, so on up to n. You label them, that's important. And then you basically add an edge between any two vertices in this set of labeled vertices. Okay, so you pick any two of them and you draw an edge between those two vertices. So any two vertices in this graph are adjacent to one another. Okay, it's called complete because all possible edges are present in the graph. Okay, and when I talk about graphs here, I actually mean simple graphs and not multi-graphs. So there are no self loops or parallel edges. Okay, so that's something that I want to sort of state at the very outset. What is the Ramsey number? So given m and l, which are positive integers, what is the Ramsey number Rm comma l? So this is defined as the smallest positive integer n, such that if you consider K sub n, no matter how you choose to color its edges using red and blue, no matter what two coloring you assign to K sub n, you will either find that you have created a red K sub m, meaning that it's going to be a subgraph of K sub n comprising m vertices, such that all the edges inside that subgraph are red, or you will find that you have created a blue K sub l, which means that you will have a subgraph of K sub n, which comprises L vertices, and every edge inside that subgraph is blue. Okay, so here is an example. You can actually show that R3, 3 is equal to 6. And here I start with 6 vertices, U1 through U6. And I basically was trying to just color them, avoiding as much as possible any monochromatic triangle, okay? Because when you're looking at R3, 3, so I should have written this probably at the very beginning that I'm looking at R3, 3. So K equal to, not K, sorry, M equal to 3, L also equal to 3. I'm looking at R3, 3, and I'm trying, therefore, you know, I'm trying to see if I can in any way avoid a red triangle or a blue triangle, like both of them. I want to avoid both of them. And I keep painting the edges with certain colors. And I find that I arrive at a situation where, you know, I haven't assigned any color to this dotted edge, to this dashed edge. But notice that it has to be colored either blue or red. And if it is colored blue, then you end up with 2 blue triangles. One is this U2, U3, U4. The other one is U2, U4, U5. If you choose to color the dashed edge with red, then you end up with a red triangle, which is U2, U4, U6. Okay, so there is no way, and in fact, you can prove this formally. Maybe this is a quick exercise for those who haven't seen Ramsey numbers before. It's fun. You can show that R3, 3 is equal to 6, which means that no matter how you choose to color the edges of a complete 6 graph, you will end up with either a blue triangle or a red triangle. Okay, so we want to get a bound on our M, M. Okay, so for those who study Ramsey theory, and this is like an extensive theory in combinatorics and graph theory and discrete mathematics in general, there have been many incremental bounds that have been obtained. A lot of progress has been made, simulations have been done, computers have been used to come up with better and better bounds. So it's possible that, you know, this bound is quite outdated, but the idea is that back then, when this was found, it was actually quite an ingenious application of probability in a problem that has no probability whatsoever so far. So what am I going to do with this, you know, this idea? So rather, what is the idea? The idea is that I'm going to resort to a random 2 coloring. Okay, so that means that every edge is being assigned a random color out of red and blue. Okay, so each edge E in capital E of K sub n, this is the set of all edges of K sub n, is assigned a color sigma sub E. Okay, so sigma sub E is a random variable. And how does it behave? What is its distribution? So sigma sub E takes the value red with probability half, and sigma sub E takes the value blue with probability half, which means that you uniformly randomly choose between red and blue and assign the chosen color to the edge. And importantly, you do this independently over all the edges, which means that the random variables sigma sub E, small e belonging to the entire edge set, E of capital N, these are all mutually independent, okay? So then what is the probability that K sub n contains no monochromatic K sub m as a subgraph? Okay, so basically I'm trying to get a lower bound on R m comma m, and I'm trying to see for what values of the positive integer n, is it possible for you to come up with a coloring? Okay, again, this links to the original question. Okay, so that basically the idea is that if you want to find a lower bound for R m comma m, then you want to find a positive integer n such that there is a way of coloring K sub n such that there is neither a blue K sub m nor a red K sub m. Okay, so there is no monochromatic K sub m as a subgraph. Okay, so what is the probability of K sub n not containing a monochromatic K sub m as a subgraph under this particular random coloring? So here's where we compute the probabilities. the probability. So the idea is as follows: you start with you fix any subset S of the vertex set V of K sub n, okay? And the subset has to have exactly M vertices, okay? Because you're looking for, you're trying to see what is the probability of not having a monochromatic K sub M. So you have to consider vertex subsets of K sub n that are of size M, okay? So now you consider the induced subgraph, which I write like this. So K sub n, and then there is this bar, and then you have the subscript S. So this denotes the induced subgraph of K sub n on S. Basically, that's going to be a complete subgraph, complete graph of on M vertices, okay? So the induced subgraph of K sub n on S, how many edges does it have? So because K sub n is a complete graph and S comprises M vertices out of the N vertices of K sub n, so it's going to have M choose too many edges, right? Because all the edges, all the vertices of S are going to be adjacent to one another, and they're totally M vertices. So M choose too many edges. So now I ask, what is the probability that the induced subgraph of K sub n on S is monochromatic? So if it needs to be monochromatic, what does it mean? It means that all of these M choose too many edges have to be of the same color. This color can be either red or blue, so you have a choice there. So that's why I get a 2 as a factor, because it can be either red or blue. I'm just asking for monochromatic, so it could be any one of these colors. Once you have chosen and fixed the color, then you need to make sure that all the M choose too many edges that are inside the subgraph induced by K sub n on S are assigned this particular color, okay? Now, as you saw in the previous slide, the assignment of these random colors is happening independently over the edges, okay? So let's say you choose to assign the color blue to every single edge of the subgraph on S, okay? That means that each edge of the subgraph on S has probability half of being colored blue, and this is happening over all the edges, happening independently over all the edges, all the M choose too many edges. So that's why you get a product, okay? Again, this is where you need to know what independent random variables mean, okay? What does independence of two events mean, for example? So that's why you get the product, so half to the power M choose 2. So now I consider the probability that there exists at least one such S, such that the induced subgraph on S by K sub n is monochromatic. What is the probability of that? So basically, the event that we're talking about here is the following. You take the union over all subsets of vertices S of the vertex set of K sub n, such that the cardinality of S is equal to M. And the event that you consider here is that the induced subgraph on S is monochromatic, and you take the union of this entire thing because you are asking for the existence of at least one such S. So that's why you're taking the union and you're looking at the probability of that. Now you use the union bound, again, something that you need to know from probability to understand this step, this inequality. So the probability of the union is bounded above by the sum of the individual probabilities. So you take the sum over all S that are subsets of the vertex set with cardinality of S equal to M outside, and inside you have the individual probabilities, okay? And these individual probabilities we have just computed here. So that's 2 times half to the power M choose 2, which is the same as writing 2 to the power 1 minus M choose 2. Okay, so and how many terms are there in the sum? So basically each term here is 2 to the power 1 minus M choose 2. So now when we are adding things up, we have to just count the number of terms, and the number of terms is N choose M, because of course you're selecting M out of N labeled vertices. So that number of ways of doing that is N choose M. So the probability that Kn contains no monochromatic K sub M is, so it's going to be this event is the complement of this event, right? So the probability of this event is going to be 1 minus the probability of this event. And for this probability, we have an upper bound, which means that we have a lower bound for the probability of the complement event. So the probability that Kn contains no monochromatic case of M is greater than or equal to 1 minus n choose m, 2 to the power 1 minus m choose 2. Okay, so we have seen that we get a bound out of probability, but the bound is on the probability of an event. What can we conclude from this? Okay, so now it comes to conclusion. So suppose n is a positive integer that satisfies the inequality. And what is the inequality? So this quantity is exactly what we saw here, this quantity. Okay, so this quantity is strictly positive. What does this mean? So this means that you have a strictly positive probability of the event that K sub n contains no monochromatic case of M. Okay, so what does that mean? Notice that the probability of the empty set is 0. So if you have an event whose probability is strictly positive, this means that the event has a positive chance of occurring, of happening. So that means that there is actually a way of assigning a 2 coloring to the edges of K sub n such that under that 2 coloring, you have neither a red K sub m nor a blue K sub m. Okay, so when n satisfies this inequality, and if you work it out, you will see immediately that this basically gives you a you are getting a sort of an upper bound on n here. So when you so m is fixed, keep that in mind. We are trying to get a bound on n, not m. M is fixed. So so because the probability of Kn under the random coloring not having a monochromatic case of M is strictly positive, that shows that there is actually, because again, as I say, the event having positive chance of happening means that the event cannot be the empty set, of course. So this means that there is actually a way of assigning a 2 coloring to K sub n such that it will contain, under that coloring, it will contain neither a red K sub m nor a blue K sub m. So you see, we brought in probability, and all we did was show that an event holds with positive probability. And from there, we concluded about the existence of a 2 coloring that gives us no monochromatic case of M. Okay, so this is how probability gets used. It's like you're trying to conclude something about the existence or non-existence of an object, and probability comes and plays a role in showing you exactly what you desire. So this tells you that by definition of Ramsey numbers, because there is a way of assigning a 2 coloring which does not admit a monochromatic case of M. So this shows that when n satisfies this particular inequality, Rm comma m is actually strictly bigger than n. Okay, so this n is not the smallest integer n for which you are guaranteed to get a blue km or a red k. Okay, so that's why I get a strict inequality here, as you can see, and this gives you a strict lower bound on Rm comma m. Okay, so let's move on to the second example and the last example of this particular lecture. So here I'm going to discuss an application to graph theory. And the idea is the following: given a graph G, again with the vertex set being capital B and the edge set being capital E, and a subset of vertices U of capital B, we say that U is a dominating set of vertices of G if the following is true. Every vertex small b which is not in U must have a neighbor small u in capital U. Okay, so this symbol means that this symbol signifies adjacency. Okay, so again, a dominating set in a graph is a subset of the vertex set of the graph. Okay, subset U of the vertex set of the graph, which we denote by V, such that if you consider any vertex which is not in the subset U, then that vertex will have a neighbor, at least one neighbor in U, okay? So I want to understand, okay, so let's say I'm looking at a dominating set of a graph. Can I conclude anything about its size? How many vertices will it contain, okay? So consider any graph G that has a minimum degree D. And here I assume that D is a, I mean, it's not necessary to assume that, but, you know, probably makes more sense if you assume that D is a positive integer. Okay, D is at least greater than equal to 1. So I want to come up with a, this should be basically it's an upper bound. I shouldn't have written like lower bound here. So I want to come up with basically just a understanding, okay, if I'm given any such graph without knowing anything else about its internal structures, can I actually find a dominating set inside it, and what will its size be? Okay, something that I can guarantee. Without knowing, again, the internal structure of the graph, except that the graph has minimum degree D. Okay, so I think maybe later on, so this minimum degree, I ended up changing to delta later on. So I'm sorry about the typo. But in any case, let me just continue because I've come so far. So I don't want to re-record this because of a small typo. So I'm going to use probabilistic method to understand this question. I try to answer this question. So the idea is, again, you bring in randomness where there is no randomness a priori. So you start by creating a random subset S of the vertices from V. Okay. And the way you create this random subset is basically you take every vertex small v belonging to capital V, you pick it up, and what you do is you toss a coin that has probability P of giving you a head and probability 1 minus P of giving you a tail. Okay. And if the coin lands head, then you include the vertex that you have just picked up inside S, otherwise you exclude it. Okay. This is the basic idea. And you do this independently over all the vertices of the graph G, which means that you sort of assume that the coin you're tossing, the tosses are independent of one another. Okay. So for those of you who are familiar with the term, this is basically what we call site percolation with probability P. Okay. So you end up generating a random subset of vertices via this method, this procedure. And let's say n or script n. This is script s and script n. So I should say script s and script n because in the next slide I have s and n. So script n, it denotes the set of all vertices of in the complement of S that do not have any neighbor in S. Okay. So n itself is also random because S is random. So n will obviously be random because you're trying to see which vertices that are not in S also do not have any neighbors in S. Okay, so here's how we go about using this, this random subset and these two random subsets. Okay, so in the next slide, let's go. So for each vertex small v in capital V, let x sub v denote the indicator random variable for the event that v belongs to script S. Okay. What does indicator random variable mean? So again, many of you are probably very familiar with this term, but for those of you who are not, this simply means that I set x sub b to be equal to 1 if v belongs to S, and x sub b is equal to 0 if v does not belong to S. Okay. Y sub v is another indicator random variable, but this one is for the event that v belongs to script n. Okay, which means that again, y sub b, you set it to be equal to 1 if v belongs to script n, and you set it to be equal to 0 if v does not belong to script n. Okay, so you have all these random variables, and please note that all the x sub v's are independent of one another, because that's how we have selected the set script s. But there could be dependence between y sub v and the collection y sub v for all v in capital V and x sub v for all v in capital V. There should be dependence between these two collections. There is probably dependence among the y sub v's as well, but none of these things will matter, because what we're going to do later on, or not later on, in the next few lines, is that we're going to use something called linearity of expectation. Again, this is something you need to know. But in case you don't, let me just state in like a one-line exposition that when you have a collection of random variables, let's say you have a finite collection of random variables, x1, x2, so on up to xk, they may have a complicated joint distribution. They may not be independent of one another, but when you're looking at expectation of their sum, that is always equal to the sum of their expectations. Okay, so expectation of summation I running from 1 through k xi will always be equal to summation I running from 1 through k expectation of xi. Okay, so that's what we're going to make use of in the rest of the slide and get the conclusion that we want. Okay, so what would be the expected size of the set S? This is not hard to see, okay, because the idea is that each vertex is being included in the set S. Each vertex of the vertex set capital V is being included in the set S with probability P. Okay, and there are totally n many vertices in the vertex set capital V. So the expected number of vertices that are included in S should be n times P. Okay, and this is what I have written here. Expectation of the cardinality of S is going to be summation V belonging to capital V, expectation of x sub V, which is the same as saying probability that x sub V equals 1, and this is equal to n times P. Okay, now we also want to find the expected size of the set script n. Okay, so recall what script n was. So script n denotes sort of all vertices that are not in script S, and they have no neighbor in script S either. Okay, so this means that for a vertex V to be in script n, what do you need? First of all, V cannot be in script S, so V was not chosen in script S. And secondly, none of its neighbors was chosen in script S either. Okay, so here this quantity dig V denotes degree of V. Okay, so degree of V is the number of neighbors of V. None of them gets selected to be included in script n, and V does not also get included in script n. Each of these events happens with probability 1 minus P, and they happen independently over the vertices. Okay, so the event that V does not get selected in script S, this is independent of the event that any of its neighbors also doesn't get selected in script S, and all of these are mutually independent. So again, you have to know what independence means, and so this you can write the probability and the intersection of these events, the intersection of the events that V is not in script S, none of its neighbors is in script S either, as the product of the individual probabilities. So for V to be in N, neither V nor any of its neighbors can be included in script S, and this happens with probability 1 minus P whole to the power degree V plus 1. This plus 1 comes because you also have to make sure that V itself is not in script S. And now notice that we have made the assumption that the minimum degree in the graph is delta. In the previous slide, there was a small typo, so I wrote D in the previous slide, but then I kept writing delta. I guess in my mind I had the symbol delta as opposed to D. So its minimum degree is delta. So degree V is at least delta, right? And 1 minus P is a quantity which is bounded above by 1. Okay, P can be any fixed real between 0 and 1. So this P that we saw here, Okay, you can just fix any real number between 0 and 1 and perform this process, this random process. So 1 minus p is less than or equal to 1, which means that when you look at the exponent here, if you replace it by a smaller quantity, then you get this inequality. Okay, so because degree v is greater than or equal to delta, and 1 minus p is bounded above by 1. So 1 minus p whole to the power degree v plus 1 is less than or equal to 1 minus p to the power delta plus 1. Okay, so we're using two inequalities here. Please keep that in mind. 1 minus p is bounded above by 1, and degree v is bounded below by delta. So this tells us then that we actually cannot probably get the exact expectation of script n, but we can get an upper bound. And the upper bound is as follows: that expectation of the cardinality of n is, so once again, we are using linearity of expectation here. This is super crucial. If we did not have linearity of expectation, if it did matter when we tried to find the expectation of sum of several random variables, if it mattered what their joint distribution is, then this computation would be far more complex and probably not doable. Okay, so but here we don't really care, because again, we do have linearity of expectation. So expectation of the cardinality of n, or the expected size of n, script n, is simply sum over all the vertices of the graph, expectation of y sub v, or probability that y sub v equals 1, and this is bound. So from this bound, this is bounded above by n times 1 minus p equal to the power delta plus 1. Okay. So, and then again, we use linearity of expectation. So what we do is, so keep in mind, the way we define script n automatically tells us that it is disjoint from script s. Okay, so cardinality of script s union script n is equal to cardinality of s plus cardinality of n. Okay, because they are disjoint. So expectation of the cardinality of s union script n is equal to expectation of cardinality of script s plus expectation of cardinality of script n. Okay, and this is bounded above by, so you simply add this with this and you get this bound. Okay, this bound, and after that you use this inequality, which you can verify by yourself in case you haven't seen, but this is a pretty common inequality that we come across very frequently. So using this inequality, you can write that the expected cardinality of the union of these two sets is bounded above by this quantity. Okay, so I'm replacing 1 minus p by e to the power minus p. Okay, okay, so now again we have found a bound. Previously the bound was on probability. If you recall, in the case of the Ramsey number example, we had a strict lower bound on the probability of an event, and here we have a strict upper, an upper bound on the expectation of a certain random variable. Okay, what do we conclude from that? So let's look at the conclusion. First and foremost, notice that this inequality holds for any p, which means that for any p, you fix the p, you perform the random procedure that I described here, the random procedure of generating the random subset script s and then defining script n after you have generated script s. And then when you look at the cardinality of script s union script n, and look at its expectation, that's bounded above by this quantity. Okay, so for every p in 0, 1, you can do this. And every p in closed 0, 1, you can do this. So now what we can do is we can try to see where this particular function gets minimized. For what value of p in 0, 1 does this function get minimized? And we find that, and you can do this using the simple calculus, to sit down and take the derivative of this expression and equate it to 0, and then see where, and then you should also see that the function should be decreasing first and then increasing, and the point where it turns towards increasing again is the point where the minima is attained. Okay, it should be the global minima between 0 1. And so you can sit down and do this exercise by yourself and find that this expression is minimized when you consider p equal to p naught, which is this logarithm, natural logarithm of delta plus 1 divided by delta plus 1. Okay, so at p equal to p naught, you have this particular lower bound. All I have done is I have plugged in this value of p in here. Okay, so just writing this instead of p here and p here, I write a natural logarithm of delta plus 1 divided by delta plus 1. Okay, and then if you do the computation, you will find that this gives us this particular upper bound. So, I mean, this n comes from this n here, which I didn't mention here because, you know, I'm just considering this function of, as a function of p. So I didn't mention n, but the n comes from the previous line, last line of the previous line. Okay. So, so we have gotten this upper bound, and now we'll have to draw the final conclusion, and the conclusion is as follows. Okay. So first of all, there is this generic, you know, something that if you know about expectation of a random variable, you have obviously seen this, that if you take a random variable capital X and let's say it satisfies the following inequality, the expectation of capital X is less than or equal to mu, then mu is some real number. Okay, so then with positive probability, X has to take some value which is less than or equal to mu. If X took values that are all greater than mu, then its expectation would also be greater than mu. Okay, so because you have this condition, so that tells us that X has to take a value which is less than or equal to mu. So we make use of that. So here we have, so this is a random variable, the cardinality of script S union script N. This is a random variable and its expectation is bounded above by this quantity. So that's why I have numbered the equation, because we're going to use the equation number here. So what this equation tells us is that there does exist, it is possible to find, that's why I write it's possible to find. It does exist a subset S. So here I'm no longer using script S because I'm now talking about something deterministic. So here's where you transition from something probabilistic and random to something deterministic. Okay, so what we have done so far, so we started with a problem that had no probability at all involved in it, and then we incorporated probability by bringing in this random subset script S and performing a bunch of computations to see what the expectation of script S union script N, what the size of this set is going to be like, so finding the average size of this set. And we got this bound. Okay, but now it's time to come back out of probability and conclude something deterministic. This is how probabilistic method works. Okay, so we saw this in case of Ramsey numbers as well. So so I'm going to go from script S to a deterministic set S. So what I'm doing is I'm combining the inequality that I have found here with this general notion to say that, okay, because the expectation of the size of script S union script N is bounded above by this quantity, then it should be possible for us to find, should exist a deterministic subset S of the vertex at B of the graph, such that now if capital N is the set of all vertices in the complement of S, such that they don't have any neighbor in S. Okay, so capital N is basically what script N is to capital S. Okay, so I'm taking the deterministic analogs now. So script S, the deterministic analog is capital S, and script N, the deterministic analog is capital N. Okay, so because of this inequality, we are guaranteed to be able to find such a subset S, and correspondingly, it's this set capital N, which automatically falls out of capital S. Once you fix capital S, capital N will be determined for you. It will be, you know, there is no variation in capital N. Okay, once you fix capital S, capital N is a consequence of capital S. Such that when you look at the union of these two sets now and look at its cardinality, then that's going to be also bounded above by this. So here is where we use this second bullet point. Okay, so that guarantees that so you can find such an S and correspondingly such an N. Now notice that S union N is a dominating set. Why? Because anything that is not in S union N has to have a neighbor in S. Okay, because N is the set of all vertices that do not belong to S and do not have a neighbor in S. So you have already included in this S union N subset all those vertices that do not have neighbors in S. So any vertex that is outside of S union N must have a neighbor in S, okay, which tells us that it must have a neighbor in S union N, and therefore S union N is a dominating set. And therefore, by this entire argument, we have found that we are guaranteed to be able to find a dominating subset or a dominating set of G, which has size at most this. Okay, it's possible that G is a graph where you can find a really large dominating set. So for example, if you look at the complete graph, you can just eliminate one vertex, and you can take the rest of the graph and take that to be your dominating set. Okay, but that is a very special and extreme case. Here I'm talking about a graph G about which you have no idea. No information is given except that its minimum degree is delta. Okay, and just from that information, we are able to conclude, thanks to probabilistic method, that we are guaranteed to have a dominating set which has size at most this quantity. Okay, N times 1 plus ln delta plus 1 divided by delta plus 1. Okay, which is a pretty nice thing, which is pretty good bound. So I think I'm going to end here. And I hope you all enjoyed this video and benefited from it. And you can, like I told you about the book. So once again, let me show you the book. The book is called The Probabilistic Method, and because this is a video that I'm making for YouTube. It's not like I'm not like just talking to my students, so I cannot just say, okay, send me emails if you have queries. So if you do have queries, you can go to this book and you can look things up, or you can just look things up on the internet. I think this course, the course in probabilistic methods, has become quite a popular one as part of courses offered in discrete mathematics and discrete probability. Okay, so it is a very interesting branch, and as I said, I would really want to continue making such videos. So I will put this on YouTube, and I will be submitting this video to 3 Blue 1 Brown. Thank you for bearing with me, and happy learning. I'll end here.